Welcome back to the students who had me last year, and welcome to anyone who didn't have me as a teacher last year to AP Physics, Electricity and Magnetism. So today we're going to begin. I'm not going to get right into the Google Classroom and all the procedures. I think at this point you kind of know what's going on with that, I hope. And then so what we're going to do today instead is just jump right to the physics of what we're going to be studying this year. So last year you learned mechanics, and in mechanics you learned Newton's laws, okay? You learned all the things that came about out of Newton's laws, like the theories of energy conservation or the law of energy, momentum conservation, rotation, so all about models of motion. Interestingly though, because of coronavirus, we didn't get to the last topic of the year, which was not on the AP, but I like to include every year because it's so fascinating, and that's Einstein's theory of special relativity, which, by the way, proves that Newton's laws are wrong, okay? The law of conservation of energy wrong, okay? So all these things Einstein disproved, and he gave us a new way, a new model of motion that's more accurate, all the way back in 1905. So we've known for over 100 years Newton's laws are wrong, physicists. But anyways, that's a little aside. Unfortunately, that's the world. We didn't have control over that, so we missed out on that very interesting and beautiful topic, Einstein's special theory of relativity. But nonetheless, models of motion. Then we dabbled a little bit in terms of forces. Now we use forces all year, but I'm not talking about like string tension or force of friction. What I'm talking about is the fundamental forces, because those forces are really different manifestations of just four different forces in the universe, okay? So they're listed here. I listed them out, four forces of nature. The strong force, okay, that is what holds the nucleus of an atom together. So you never feel the strong force. When you're touching things, you're touching the outside of the atoms. You can never reach into an atom with your body, okay? So you never experience this. It's gluing the nucleus together. This one I'll skip for a minute. This is also in the nucleus. It comes into play when atoms fall apart. And then the gravitational force, this is what I mentioned. We studied this a little bit last year, or actually in a fair amount of detail. There's this universal law of gravitation, which I mentioned was thought of by Isaac Newton. So all forces that you experience in your life fall into these four categories. I eliminated two, and we know about the gravitational force. So that's like your body weight. So that leaves out a lot of different forces that you experience here. The electromagnetic force. This turns out to be responsible for all five of your senses. So it's important in terms of your personal experience. For example, touch, okay? I already mentioned that briefly, that when you touch something, you are not touching the nucleus, you're touching the electrons of the atoms. The electrons in the atoms of the atoms in your hand get close to the electrons in the atoms of the thing you're touching, and that creates the sensation of touch. So electron repulsion is an electrical effect. Okay, so it's part of the electromagnetic force. Okay, so taste. You put salt crystals on your tongue. Oh, it's salty. Okay, so you have that sensation on your tongue. That's when the ions of sodium and chlorine break apart, charges plus and minus, and they start touching the nerves on your tongue and interacting as positives and negatives attracting. That's the electromagnetic force. That's taste. Smell works in a similar manner. Molecules go up into your nose and electrically interact with nerve cells in your nose. Hearing is atoms, air molecules that are vibrating against your eardrum. So again, the electrons of one atom get close to the electrons of your eardrum atoms, and it repels and causes your eardrum to recoil. Now you hear sounds. And the last one is sight, which is light. And we're going to learn in this year that light, the fifth sense, is vibrating electric and magnetic fields. Okay? So all five senses, okay, right here, it's a huge, important force. If you want to understand the universe, your experience, you've got to understand this, okay? Also, anytime you turn on any electrical device, there are electrons that are coming out of the battery with chemical reactions, and those are going through the device, maybe like your cell phone or your computer, and they are stimulating things, and that's the electromagnetic force. Generating electricity involves magnets and wires and charges. So this is huge, okay? And we didn't learn about it last year. And that is the focus of the entire year this year. The electromagnetic force, APC, electricity and magnetism, and then we'll put them together at the end with electromagnetism because they're linked together. It may seem like a magnet is different than an electrical force. They are connected. You cannot separate the two phenomena. It's one electromagnetic force. So that's what we're studying. And it brings me to the shirt I'm wearing. Okay, so every year I wear my famous, or whatever, maybe not so famous, but my Maxwell's equation shirt. This is just something that someone kind of made in a little like a cute science, maybe science nerd sort of created this shirt. So I will, I got to go on my tiptoes. Well, maybe I don't want to move the camera because, hold on. I got it lined up to the board. So stand on this. Okay, so you can see it said, this is basically a play on the Bible passage in Genesis, and God said, let there be light, and then there was light. So this basically says, and God said, and then you see all these equations, and then there was light, okay? Because these are the equations that describe and explain how light actually works, okay? It's basically vibrating electric and magnetic fields satisfying these crazy equations. So that's basically the meaning of the shirt. By the way, it is school and we're not supposed to be, preaching religion. I will say this, that physics doesn't really have technically a view on religion. Some people say, oh, it's science. They believe that there's no such thing as God or whatever. Well, there are very prominent atheist scientists who believe, based on their science, that God doesn't exist. And then there are very prominent scientists, famous ones, that believe, based on what they know of physics, that there has to be a God. So me saying this, I'm not even taking a position. Probably the most well-known is Albert Einstein. Really seriously believed in God and talked about it in his science work, about what God was thinking and this and that. So, I think it's okay because I'm not saying one way or another. It's just sort of showing that, this is light and kind of trying to show you the power of these equations. But again, if you look here, you can recognize integral symbols, two integrals, derivatives. So the language of electromagnetism, understanding this topic, you cannot understand it without calculus. So that's where we begin today, with a review of calculus. Okay, that's why if you look at the unit plan, it says mathematical requisites, okay, calculus. I think I got it here. Nope, I didn't bring it down with me. Okay, that's all right. Well, you see it in the stream, you could look it up. So I'm going to erase this and we're just going to go over some basic properties of derivatives today. If I find my eraser. I'm going to write out the rules, basic rules for taking derivatives. Remember, a derivative is a rate of change. Okay, so the first is the simple power rule. If you have y equals ax to the n. So this is just like a constant, like maybe 3 or something like that. Oh, camera's out of focus. Okay, so maybe it's like 3 or 5. And this is also some power. Maybe it's x squared or x cubed. The way you take the derivative dy dx will be that constant times the exponent and now the function raised to the n minus. So you bring the coefficient to the front, and maybe this is like 3x squared, so you do 3 times 2 or 6, and instead of x squared, x to the 1. Real basic rule. Okay. Another rule is if you have the natural log. Then the derivative the constant stays the same, and you just do 1 over x for the derivative of the natural log. The next one. The exponential function. This is an interesting derivative. Oops, I forgot the equal sign here. It's just the exponential again. And then we have a couple trig functions, a cosine of x if you take the derivative of that with respect to x, you get negative sine. And if you want to take the derivative of the sine function, okay, it's just the cosine function. Okay, so some basic rules. Again, it tells you how fast y is changing when x is changing. A lot of times we have time, so how fast something is changing with respect to time. But today I'm just using x to get the rules down. Well, as you might remember from last year, very often we don't have just simple functions like this. We have functions within a function. And then what we need is what's called the chain rule. If, for example, we have y not as a x to the n, but some function to the n power. Like maybe we have parentheses here, and this is x squared plus 3 or something in there, this f. So we've got a function within a function. The way to take the derivative of this is, like before, you use the power rule, which means you're going to put the n in the front and subtract 1 from the exponent. Okay, but we're not done. What we have to do now is we have to multiply by the derivative of that function. Okay, let me just check and make sure that's visible. I think it is. Okay, good. And I'm going to, do these derivatives all over again, but replacing x with a function. So for example, if I have not log of x, but log of f, again, maybe f is like x squared or something, so log of x squared, then the derivative of this function, again, the constant just stays there, doesn't affect the derivative at all. But we use the rule. So we put 1 over f instead of 1 over x. But now, when we're done, or we're not done yet, to correctly evaluate this, we multiply by the derivative of that function inside the log. So I'll do examples later, but like, for example, log of x squared. So you put x squared down here, and then multiply it by the derivative of x squared, which is 2x. And now you have the log of that function. Same here. We do the same kind of procedure. If there's a function like x squared in the exponential, then the derivative, the constant a remains. We have e to the f again, because that's the exponential. The derivative of the exponential is just the original function, but we need the chain rule. We multiply by the derivative. Quickly just do the cosine and sine. A cosine of f, the derivative is negative sine df dx. And last one, the derivative of the sine, but if there's a function in the sine, okay. So there they are, the rules that we're going to be practicing now with some examples. So you can obviously pause this video to make sure everything is jotted down. And I am now going to erase, but again, the goal here is to practice our calculus rules so that we can eventually, at the end of the course, finally understand Maxwell's equations. All of electromagnetism. Okay. But before I do some examples, I just want to remind you the significance of these when you're looking at a graph, the significance of derivatives. So let's suppose I'm just going to make a function that looks something like this. This is some kind of x to the third function with x squared and x and maybe a constant in it. And then you could get this sort of, maximum minimum kind of relationship. So at this point right here, maybe I'll make this. This is point A. At A, what's true is the derivative is 0. Oh, I forgot y and x. dy dx equals 0 at that point. What's also true is if you take the derivative of y twice, we write that, if you remember, with squareds. D squared y, well, maybe I should make a little more space here, and dx squared here is less than 0. In other words, when the second derivative evaluated at a point on the graph comes out to be negative, that means the function is concave down. Okay? Let's take another point here. Maybe I'll do here. Let's call this C, and I'm going to put B in the middle there. So at C, here as well, the derivative is 0 because the derivative is the slope. So here the slope is 0. Here the slope is 0 also. So we can say that the derivative or the slope of the graph is 0 at the minimum as well. But if you were to evaluate the second derivative of y with respect to x, you would find that you'd get a positive answer here. So when the second derivative comes out positive, the function is concave up. And then the point right here in the middle, which, as I said, I would label B. At that point, the derivative is obviously negative because the function's going down. But the important thing here is that the second derivative is 0. That's what we call an inflection point. Inflection. The point at which the function changes from concave down to concave up. So this is some of the information you can find out about a graph from its derivatives. All right, as I said, let's take a look at a couple examples. This should be pretty easy for you, I think, this example coming up, because you've probably been doing it for close to 2 years now. 4x cubed. So, a simple function, 4x squared plus 4x cubed plus 7x. So here, we take the derivative of y with respect to x. And essentially what we're doing is we are doing the power rule on this and the power rule on that. So we can say that this is 4 times 3. We bring the exponent to the front, and then we subtract 1 from the exponent. And then here, we bring this 1 power, okay, to the front, and then we subtract 1 from the exponent, which gives us 1 minus 1 is 0. So in other words, dy dx is 12x squared plus 7, okay, following the simple power rule on these two functions. Okay, example 2. Let's say our function is a this time, not y. We could call it whatever we want. Okay. Okay, now you see we've got a function inside of a function. Make sure. Okay, yes, that's visible. Okay. So we have to use the chain rule here. So in order to take the derivative of this function a with respect to x, this constant here doesn't affect the process, but I take this 9 and I bring it to the front. And then I take this function and I subtract 1 from its exponent. So 9 minus 1 is 8. Okay? And then, well, that would be the case if I just had x to the 9th power. I'd be done, but I'm not, because I have a function in here. So what I have to do is multiply by the derivative of everything in the parentheses. So what I do is I take this 4 and I multiply by 3 and then subtract 1 from the exponent. So that's 4x cubed, the derivative of that. And the derivative of 7 is 0. The derivative of any constant, well, constants don't change. So derivative is all about change. There's no change. And I could just touch this up a little bit. So I've got 12 here times 18 gives me 216, I think. 216. Oh, maybe I'll put the x squared with the 216. Why not? Okay, so there is another example. Okay. Let's take a look at another example. Negative 5t. Oops. What was it? 4 negative 5t to the 4th. Okay. So again, I've got a function inside of the exponential function. I need the chain rule again. So now I could say dy dt this time. It's a function of time, so I change from x to time. Okay, I'm taking the derivative with respect to the time. So the derivative of the exponential, once again, is just the exponential. But now I need to multiply by the derivative of what's inside the exponential, which is negative 5t squared. So t to the 4th. So t to the 4th, I bring the 4 to the front, and then I subtract 1 from the 4th power. So this gives me negative 80 t cubed e to the minus 5t to the 4th. Okay. Another example. Okay, example 4. Let's say a equals 1 over 3t squared plus 1. Okay. Okay, so now this may look confusing. Maybe you say, we never did anything with something in the denominator like that. But what we could do is we could rewrite this as 3t squared plus 1 to the negative 1 power. And then what we could do is just follow the power rule again with the chain rule together. So d of our function a with respect to time, you're going to bring this exponent to the front, -1. Subtract 1 from the exponent, -1 becomes -2. And then you're going to multiply by the derivative of everything inside those parentheses. So that's going to be 3 times 2 t to the 1 power. I bring the 2 to the front and I subtract 1 from the exponent. And then the derivative of 1 is 0. All right, so now I'm going to touch this up a little bit and rewrite dA dt. I have a negative sign, and then in the top I've got 6t to the 1 power, which I could just write as 6t. And in the bottom here, because of the negative power, I've got 3t squared plus 1 squared. Okay, so there is the derivative of that function. Okay, and let's do a trig function now. Okay, so there is my function. Once again, I've got to use the chain rule because I have a function inside the cosine, not just a time variable. Now, normally the derivative of the cosine is the negative sine function. So I do negative sine but I need to multiply by the derivative of everything inside here. That's the chain rule. So the derivative of 5t cubed, I move the 3 to the front, and then I do t squared and then the derivative of 3 is 0. It's a constant. So 15 times the 4, or the -4, gives me -60 t squared times the sine of 5t cubed plus 3. Okay. And I want to do one final example. Maybe I'll do it here. Example 6. Okay, so again, we don't have a log of time, we've got log of a function. So we use the derivative for the log that we know, which is 1 over x, right? So we do 1 over the function. And then we multiply by the derivative of all of this, which is 3 times t squared plus 0. So what we have at the top is 6 times 5, or 30 t squared over that in the denominator. Okay, so that is derivatives. Okay, so tomorrow we're going to review some basic integration And then this topic only lasts a few days, and then we're going to take a quiz on derivatives and integration on the basic calculus before we move on to the physics. Okay, so we're just warming up by reviewing calculus. So a reminder from last year, copy all these notes. I'm going to do something a little different this year where there'll be 2 assignments, one for you to submit photos of your notes that you took, and that'll be part of the credit for the class. And then the second assignment will be the homework problems. Submit photos for that. And that'll be the assignment. And then remember, there's going to be a Google Sheet at the end that will have everyone's name going down one column, and then across the next column will be today's homework. And then in that Google Sheet, suppose you had questions on 2 and 4. And so you would put next to your name 2, 4, and that lets me know that those are the questions that you had trouble with for me to go over. And if you have no questions, you're still going to enter something into that Google Sheet. You're just going to put an X next to your name in that assignment column. Okay, so I hope you enjoyed your first physics class. I did, okay? And I'll see you tomorrow.